This is the lecture for Module 4 of Unit 6. Module 4 continues talking about spontaneity, introduces the second law, and the Gibbs energy. Okay, now that we've talked about entropy, we can discuss the second law of thermodynamics. Formally, mathematically, it can be shown that for any change, the entropy change of the universe must be greater than or equal to 0. So the entropy change of the system, whatever we're looking at, plus the entropy change of the surroundings must be greater than or equal to 0 for a process to occur. You may hear and you may have heard talk or a discussion about how entropy is always increasing in the universe. Let's consider what this means for our purpose, and we will use this information to define the Gibbs free energy. Consider a system with constant pressure. Q for the surroundings is the negative of delta H for the system, since delta H is equal to Q. If we assume a constant temperature, the entropy change of the surroundings can be taken as delta H over T if we have a constant temperature. We've talked about how delta S is often for heating something up, Q over T at constant T. Means the total entropy change of the universe is the entropy change for the system minus delta H over this for the system over this temperature T. Right, if we multiply through by the constant temperature T, assume the temperatures of systems or surroundings are the same, T for the delta S total of the universe is T delta S for the system minus delta H for the system. All right. Criterion for spontaneity is delta S total has to be greater than 0, and since T is absolute temperature Kelvin in this formulation, T delta S must be greater than 0 as well. All right, so the left-hand side must be greater than or equal to 0 for a process to occur. All right, that means that the right-hand side must be greater than or equal to a process to occur. So if we take the negative of the right-hand side, delta H minus 2D T delta S, that must be negative for a process to occur, for the process to be spontaneous. Therefore, for a process to be spontaneous at constant temperature, delta H minus T delta S must be less than 0. Delta at constant temperature and pressure, delta G is delta H minus T delta S. This is a definition of delta T, and that must be less than 0. We should note that formally we can define G as H minus TS. However, what will concern us in this course is the change in G, which will be delta H minus T delta S at constant T and P, and this must be less than or equal to 0 for a process to be spontaneous or a process to happen. The quantity G is often called the Gibbs free energy, quote unquote, and the quantity delta G is the change in the Gibbs free energy, or the free energy change, you will often hear it called. All right. Let's consider this condition, delta G minus delta H equals delta H minus T delta S is less than or equal to 0. Alright, this whole equation or condition holds at constant P and T, and this means a process tends to be spontaneous if delta H is less than 0. If this is negative, it will tend to make delta G negative. And if delta S is greater than 0, if delta S is positive, since T is always positive, that would also tend to make delta G more negative. We've already discussed both of these observations. Processes that are exothermic tend to be spontaneous, and processes in which the entropy of the system increases tend to be spontaneous. You can view this condition as showing how both exothermic processes and entropy increases can come together to make a process spontaneous. As I say, if you want to know more prosaically, if you want to know if a certain reaction can happen, you can find its delta G. If it's negative, it's spontaneous. At least from a point of thermodynamics, it's possible to get the reaction to go. Now, how can you find delta G for a chemical reaction? Well, much like enthalpies of formation, you can use standard Gibbs energies of formation to find standard Gibbs energies of reaction. Right, this works exactly like using enthalpies of formation, including, by definition, the Gibbs energy of formation for elements is 0. So let's look at a straightforward exercise. Find delta G for this reaction, which is the combustion of methane to make carbon dioxide and water vapor. It will be at a temperature of 25 Celsius. And here are shown some tabulated values of Gibbs energies formation for CH4, CO2, and H2O. You should attempt this exercise before continuing in the presentation. Alright, let's look at our solution. Find delta G for the combustion of methane or natural gas, given these delta G's. Alright, all that happened, we take delta G of formation for 1 mole of carbon dioxide, negative 395 kilojoules per mole times 1 mole. Add that to 2 moles for water, 2 moles of water times delta G for water, which is negative 228 kilojoules per mole in the gas phase. Subtract, because we have to subtract reactants from products, 1 mole times negative 56 kilojoules per mole for the methane. And notice oxygen does not appear in this computation because it is an element and has a delta G of formation of 0. Alright, the answer is that delta G for this reaction is negative 800.4 kilojoules. Note, here we have a negative value for delta G, and we expect this reaction to be spontaneous. And since we know we burn natural gas for heat in our homes, we know that this is a spontaneous reaction. Okay. Let's take a moment to think about how temperature can affect spontaneity. Delta G is delta H minus T delta S, and delta G must be less than or equal to 0 for a spontaneous process. All right. Clearly, if delta H is negative and delta S is positive, delta G must be negative no matter what T is equal to, since T is always positive or 0, and the reaction is spontaneous at all temperatures. So if it's exothermic and the entropy is increasing, the process or the reaction will always be able to go. If, on the other hand, it's an exothermic reaction and delta S is less than 0 or negative, entropy is going down, then it will only be spontaneous at low temps. If delta H is negative that can be offset by the positive delta S if T is large enough. So T must be small enough so that delta G remains negative. If delta H is 0 and delta S is greater than 0, T must be large for the delta G to become negative, and the process is spontaneous at high temperatures. If you have an endothermic reaction where the entropy goes down, delta G can never be negative. The reaction will not be spontaneous at any temperature. Let's consider this in relation to something, well, a common phenomenon, melting or boiling of substances. Right. The boiling point occurs of a substance such as aluminum occurs when the process for going from a solid to a liquid is in a state of equilibrium, or equivalently when delta G is equal to 0. Delta G is equal to 0 means both the forward or the backward process can occur because, well, delta G is 0 for both the forward or backward processes. Right, since delta H, G is delta H minus T delta S, we can solve for T at delta G equals 0. We consider delta H and delta S constant. Alright, 0 is delta H minus T delta S implies that T is delta H over delta S. Alright. Delta H for this reaction, according to tables, is 10.7 kilojoules per mole, and again, also according to tables, delta S is 11.5 joules per mole Kelvin. These will be values at 25 C, but we're assuming they're constant. Therefore, I can find the melting temperature as delta H over delta S, and this calculation gives me 930.4 Kelvin, or 657.3 Celsius. Experimental value is 660.3 Celsius, so we have a small error of 3 degrees, which is roughly 0.5% or so. Alright, note that if T is below 930.4 K and you plug in delta G is delta H minus T delta S, you'd get a positive number. Delta G is positive. Melting is not spontaneous below the melting point. If you have a value of T greater than 930.4 Kelvin and plug in the delta G is delta H minus T delta S, you'll have a value of delta G less than 0 or negative. Right, so at the melting point or temperatures above the melting point, melting is spontaneous. In fact, above the melting point, only the liquid can exist. It can be shown that there is a relation in any reaction between delta G and the equilibrium constant K. When you calculate a standard delta G from data tables, the standard delta G gives you a delta G from going from pure reactant to pure product. Mixing reactants and product increases delta S for the system and lowers delta G. In other words, pictorially, here we have a profile of G versus, well, for a chemical reaction versus amount or mole fraction of product relative to reactants. So over here on the left-hand side we have pure reactant. Over here on the far right we have pure product. The difference between this value of G, higher on the y-axis, and this one lower on the axis, is delta G for the reaction from the data tables. Note that since this delta G is greater than 0, we would call going from here to here not spontaneous. However, mixing reactant and product lowers delta G, which means that somewhere in the middle will be the lowest possible value of G. Okay, it can be shown that the standard delta G is equal to negative RT times the natural log of K, where K is the equilibrium constant. For gases, this K that you can calculate is Kp. For solutes, the K that you calculate from the data tables is Kc. Right, what this will show is that if delta G is negative, you have large K. The reaction is expected to go to the right. For positive delta G, you have small k. The reactants are favored. In other words, for quote-unquote non-spontaneous reactions, K will be small and the reactants will be favored. For spontaneous reactions, K will be large and the product will be favored. Right. Consider going from liquid to vaporous water. At 25 Celsius, you can calculate delta G as positive 8.7 for this process. In other words, it's not spontaneous because delta G is positive. And that makes sense at 25 Celsius. At 25 Celsius, we know water doesn't boil. Okay, if we can take this value of delta G and calculate a K value for this process. Natural log of K is negative 3.5 if we make this calculation. Notice that we use joules for delta G, the joules value of R in the denominator, and the temperature is Kelvin. Obtain natural log of K is negative 3.5. K is 0.030. Alright. The equilibrium expression for this reaction in terms of Kp is just the vapor pressure of water. So K, 0.030, is just the vapor pressure of water. So the vapor pressure of water at 25 C is 0.030. Remember that Kp involves pressure in atmospheres. We can convert this to torr if we want. It gives 23 torr. And the experimental equilibrium vapor pressure of water agrees with this calculated value. It's actually found to be 23.8 torr. All right, let's consider another example. N2H4 and 2O2 goes to 2 NOs and 2 H2Os. Find K at 25 Celsius. Given these values for delta G of formation for these substances. Attempt before continuing. All right, the delta G calculation is a products minus reactants calculation. NO and H2O are the products, and there are 2 moles of each of those. We find delta G values for these in data tables. Here are the corresponding values for the products in kilojoules. For the reactants, we again neglect oxygen because its free energy of formation is 0. And into H4 are calculation. For 1 mole of N2H4, we obtain a value of positive 159.3 kilojoules. Alright, take 173.4, subtract 457.2, subtract 159.3, and get a value of delta G is negative 443.1 kilojoules. I show that here converted to joules. Alright, now this negative G value should tell you, or would lend us to predict that this reaction will be spontaneous. In other words, if we just start with reactants and get this reaction going, it should go. Since it is spontaneous, we anticipate a large value of K. The right-hand side, it's for a spontaneous reaction, the right-hand side is favored. If we use natural log of K as negative delta G over RT, we take the negative of 443,100 joules, divide by the joules value of R times 298 Kelvin, get a value of 179 for the natural log, drop moles quantity, so that, because natural logs are unitless. Taking the inverse log gives K, which is 5 times 10 to the 77th, a very large value of K. This concludes the lecture on spontaneity and Gibbs energy.